Hello and welcome to my talk on building a centralized knowledge graph to power your analytics. I'm going to start my presentation by introducing myself a little bit. So I'm Alex Ridden. I've been working for about 10 years in industry where I've built advanced analytical models and utilized network graphs, a lot of the time generating features for those models. I'm particularly specialised in applying network graphs in the detection of financial crime. I worked in lots of different multinational banks and insurance companies. I mention that because I think that my experience with trying to integrate analytics with legacy systems and challenging data models is kind of relevant for this topic. And I founded Knights Analytics a few years ago, originally just to be a freelancer, but during that time I actually built some software that I now sell full time. So I'm going to start by talking about what a knowledge graph is and why you might use one. The bulk of my presentation will be about like how you should build a knowledge graph and a lot of the considerations and challenges you might face when you try to do that. And at the end, I'll go through a kind of cheeky plug of my software. So what is a knowledge graph? The truth is that the definition of this seems to be quite varied and vague depending on who you speak with. And so for the sake of this presentation, I'll use my own definition. And that is that a knowledge graph is a unified evolving data store, which is organized into a queryable semantic graph. And it enables kind of technical and non-technical individuals to utilize a wealth of knowledge. But there are a few things that are, I guess, universally accepted about knowledge graphs. First, that it should have a graph structure, and that graph structure should be well defined, meaning that the entities, the types of relationships, and the attributes are all understood and concrete. And then the next thing would be that a single node aims to represent a one real world entity, object, concept. Obviously, that's not always achieved, but we'll talk about how you can achieve that. And then finally, that your graph is continuously growing and evolving, both in terms of how much data it can ingest, its volume, and the schema. So why is this useful for analytics? This first diagram, I think, outlines a common problem that a lot of data scientists and analysts face every day. So we're often starting by thinking about a business problem and then have to go and find the data that we think can help solve it. And oftentimes that data, even if it's within a data lake, is quite siloed. So the data sets that you might want to combine have different owners. There's probably one person in your organization that knows about it really well, and you have to go and talk to them a lot. But you want to essentially then find it, write these queries to extract it, and then spend a lot of time joining, manipulating, and transforming it. There's lots of numbers floating around about how much time data scientists spend doing those three tasks before they can then actually create their models. But regardless of what that percentage is, it's definitely considered one of the most frustrating and time-consuming elements of their job. So I think that the knowledge graph can be really useful in that every time that you need to start to combine, process, and engineer your data into something usable, you can actually put it in this centralized store and start building up connected data that can be used by other people within your organization, where they can query it and integrate it into dashboards or just download it if they want to start analyzing it. And there's all sorts of kind of iterative effects of being able to do that over time. So apart from that, there's also a lot of really practical reasons why I think knowledge graphs can be powerful for analytics. The first one being that you get a much more complete view of an entity and their interactions with other entities, and also all of their attributes are in one place. So instead of kind of going to many, many different data sources and having to find out where you can find certain pieces of information, the idea is that in a knowledge graph, it's already there, it's already defined in a way that you can understand what it is as well. And then once it's in a graph, especially if it's in something like Dgraph, you have a nice query language where the query itself is very intuitive. So even if you're not a particularly technical person, you can understand that a query like individual has address will return to you the addresses that an individual has. So aside from those things, of course, graphs are often used in visualizations, so why not store your data in such a way? And I think those of you familiar with Dgraph will have already used Ratel in order to be able to like navigate and interpret your data and find it much more intuitive oftentimes than just looking at rows of data. And that kind of leads into the integration with web apps and BI tools being quite straightforward. And then finally, if you actually generate features on top of that graph and store them back in the graph, you can start to treat your graph as a kind of feature store or an object feature store, so that every entity or relationship within your graph, you can start to enrich it with the queries that you might be running on top of your graph. So I want to talk about a use case that I think's really poignant. So I've worked in many financial institutes, as I mentioned before, and what people who don't work in my industry don't really realise is that a lot of the times even similar problems are often siloed. So what I've got on the screen here is like two oftentimes separately handled use cases. On the left, you've got a transaction monitoring situation where a victim's account has had all their savings drained into a mule account, and that mule account has then sent those savings on into the ether of international banking transactions. And on the right, you have a money laundering use case, which is often in the corporate world and often requires slightly different data, but it certainly is often tackled differently. So the models running on that data are separate, and the people who work on those things are often separate within the bank. But if you integrate some other data that might come from your cybersecurity department, such as device information, this type of information is often used in one or the other of these use cases, but often not as a connecting factor between them. But you can imagine that if you have a high risk transaction that comes from a device that is then used by a company that seems to be part of an investigation into anti-money laundering work, then of course it helps build your case and understanding around that investigation. So on to the meat of this presentation. How do you actually build a knowledge graph? What kind of steps do you have to go through, and what are the challenges that you will face? The first thing will be to design an ontology. An ontology you can think of as a schema, but with a few extra caveats. How do you incorporate a semantic ontology into a database like Dgraph? How do you actually go about deciding what your node types versus your attribute types are going to be? Once you know that, how will you map your data, extract those triples and quads from different data types? And how do you actually reconcile different entities and recognize that they are in fact the same representation of a real world person or business or address? And once you have all those things, you of course want to start loading them into a graph, and you probably want to build that graph up over time, which is a very different problem from bulk loading your data, which a lot of people have experience doing, but not as many people have experience actually productionizing a graph and using it next to their kind of data lakes or other data sources. And of course, all those mapping, resolution and loading into the graph steps are going to be continuous and hopefully alive. So once you have all those things, there's of course consuming data from that graph, and then a few different things that you should think about in terms of your solution, such as, do you want to have multiple graphs or one graph within your organization? How can you potentially combine data across these privacy boundaries, where it could be really, really useful to share data, but you're not allowed to, for example, because of GDPR here in Europe. So yeah, I'm going to dive a bit more into all those topics. The first one being the designing of the ontology. So firstly, you will have to model your data as an ontology, and there's some subtle but important questions that you'll have to ask yourself here. So my first example is, when you have a person with a passport, is that passport a kind of attribute of that person? Would you consider the passport ID an ID of the person, or would you actually like link a person to a passport object? And with that object then have, you know, the start and end date? Is it possible that it can be linked to more than one person? Is it possible to have or to handle it when a passport goes missing? Things like that. And then I also want to talk a little bit about how you can incorporate semantic ontologies into Dgraph, more specifically about semantic reasoning and logic and rules. So when you're defining and designing your ontology, there are a number of steps that I think are important to outline and consider. So the first one is, of course, answering a business question, or at least understanding what applications you want to use your graph for. And once you know that, you want to start searching for data sources. So here we have an example of customer data where a business has an account, and there are various things that you know about that relationship, like the start and the end date and the account number and the bank that it's associated with. Once you have those kind of triples or quads defined, then you'll also need to kind of build out almost a blueprint of all of the relationships and all of the attributes that you can possibly have in your graph. And the final and one of the most nuanced pieces of defining an ontology is also rules or business logic that you can apply based on the relationships that exist. So here's an example of where one business is a parent of another business, which means that you can infer that both businesses are part of the same business grouping. And I'll show you some examples during the mapping of the data as to why that's important. But a few things to note here are the ontology means that you have like a very strict definition of what can and can't be included in your graph. So your schema shouldn't just adapt to new data concepts that haven't been well defined. However, it's also important that your schema should be able to evolve over time. So let's have a look at mapping. So there's two main challenges that I've highlighted here. One is the mapping unstructured data. So this isn't something I'm going to dive heavily into because there's you know, many hours of work that can go into this particular topic. But I'll show you a bit about what it looks like when incorporated into the graph with other triples. But the kind of interesting concept about knowledge graphs is this inferred logic and business rules that you can apply to the graph structure. So here we've got three examples that I put together to walk you through an example of what building up a graph from different data sources can look like. Firstly, we've got some customer data where you have an account ID, a company name, the registered date of that company and the account date. And that represented as a triple in your graph would be, you know, business has account linking to an account. Let's say you have a news source which comes in, and you can use some natural language processing, such as named entity recognition, in order to start pulling out some of your triples here. So here I've got Umbrella Corp recently acquired Acme, and then that can be represented as the business acquired another business. And then finally, we've got company registrations. So a completely different company that we haven't seen yet. Virtucon is the parent of the child company Umbrella Corporation. And we've got some founding dates, but that can be represented in this way. A business is a parent of a business. And if we take that data and we just take very simply the names, then we assume that these are the triples that we get from my example. And once you load them into the graph, I think there's going to be some connections found here, which I'll dive a bit more into in the next section. But essentially, we've got Acme Inc. and Acme, and we believe they're the same, and Umbrella Corp and Umbrella Corporation we think are the same. So when you load them into your graph, it will look something like this. But the interesting part is where the rules come in. So since Virtucon is a parent of Umbrella Corp and Umbrella Corp acquired Acme, we can infer that Virtucon should be considered a parent also of Acme. And all three of those companies, because of this hierarchy and structure, we might want to say belong to the same company group. And if a company group inherits the accounts of the like child companies, then you might also be able to infer that that company group has this account. You can see how we've taken a relatively simple structure and we've kind of built up some extra links and nodes into it. But back to the point that I just mentioned, which is around the resolution of entities and how do you actually disambiguate your data? How do you start to collapse nodes together? So I have another example of why entity resolution is so important. Here's an example where we have 2 transactions for completely separate accounts, and each account having an individual associated with it and addresses. And those addresses, if you resolve them, we determine that A and C were the same and B and D were the same. And so we've got this kind of ring-like structure where we can see that there's some connections already. And if we take that information, we might also recognize that 3 of these individuals are in fact the same. And so we've got some individual resolution. So the story has changed quite a bit from the original graph, where now that first transaction looks like money being sent to just another account owned by the same person. But the second transaction is now money being sent to someone that this person apparently lives with, or at least has registered at the same address. You can see why this would become very important when you're trying to follow money flows or when you're trying to determine the risk of a transaction. Disambiguating or resolving entities in particular is key to having effective models and features. So what are the challenges in doing this? Well, I think the most important one is that all identifiers have uniqueness problems, and some of them you might assume that they're not a problem for you, and a lot of them you'll find that are a problem. So I've even been a kind of victim of this myself. When I registered at my bank, I was registered as Mrs. Alex Ridden, but when I registered my business, someone accidentally entered Mr. And that actually meant that I couldn't connect those 2 accounts into the same app, and I wasn't able to actually log into both my business and personal account in the same interface. So it was not a great customer experience. But as you can imagine, as well as just human error, there's all sorts of other errors. So IBANs are not universal, even though within Europe we consider them quite unique. And phone numbers get reused. And of course, you've got country codes. Address formatting is a very challenging topic that many people have spent many years trying to solve. And there's great solutions for all of these things. There's all sorts of resolution options available. And ultimately, you're really trying to answer that question of what about combining data that doesn't even have a key, or especially when you're combining internal data with external data sources or data sources that just don't have the same information available. So I wanted to just go over some of the options that are available to you if you're doing entity resolution. The first one is the most obvious one and one that most people use, which is ID matching. So I've seen countless graphs built within companies where they simply just match on the bank account number. And like I mentioned earlier, account numbers get reused, but also one person can have many accounts. And so treating them as a single node attached to an individual, if you don't resolve those individuals, you never really quite get the full picture of all of their transaction history. So the next step for anyone who's spent a lot of time doing this type of thing is to do rule matching. An example of which would be in the UK, we have postcodes which are quite unique in that you only need the postcode combined with a street number to be able to identify a single address. That's not the case, obviously, internationally. And so you'd need completely different rules if you're trying to deal with international address resolution. And then the most advanced and newest versions of entity resolution combine machine learning and graph-based features in order to be able to determine which entities are likely to be the same. So once you've done all this, or hopefully maybe even before you've done all of this, you want to consider a number of things when it comes to productionization and architecture. So I just want to go over a few of the challenges. I don't have universal answers for everybody, but at least this might give food for thought when you're thinking about developing a knowledge graph for your company. So the first thing will be how on earth do you integrate with the existing ecosystem? We've got a nice XKCD slightly edited cartoon here, which just it reiterates a problem that is found in almost all, especially large companies, where lots of initiatives take place, especially around a similar time, and we end up with many, many different solutions to the same problem. And you want to think about, are you going to build a knowledge graph that's just essentially another data silo that's not actually solving the problem of combining data across your organization? Should it be a layer on top of like existing data lakes? Is it itself like a new form of a data lake? These are all questions that are challenging to answer because there's things like, is your resolution universal, or do different projects and different business parts of your business require different permissions and different types of resolution? How are you going to go into production? We've got lots of challenges around scaling, which happily Dgraph solves a lot of our issues for us. But you also need to think about ingestion of new data. How are you going to collapse multiple nodes? Are you going to keep a history of updated data points? And then related to that is, of course, updating, deleting, and streaming any new data in, and being able to infer or apply some of this semantic reasoning and logic to it that I mentioned earlier. And then finally, of course, operational challenges, kind of boring stuff, but important stuff: access control, backups, high availability, upgrades, etc., etc. So, of course, here at Dgraph Day, we want to talk about all of the problems actually that get solved by using Dgraph as part of your solution. And we've certainly enjoyed being able to utilize all of these benefits whilst building our application. So a lot of our customers particularly interested in Dgraph now being cloud hosted. That's great. And GraphQL being super easy to integrate with front end and easy to query by our clients. And scalability and DQL itself we use with gRPC for kind of internal speed and query flexibility, and being able to know that you can store more data and increase the amount of queries that you can respond to. Being graph native was super important for us when we were building our solution, and Dgraph really allowed us to have the graph database both as a data store and a query engine. And a lot of Dgraph's enterprise features addressed a lot of the operational requirements that I mentioned earlier. So a few other considerations. You want to think about how many graphs you should build. There's all sorts of questions. I can't go over all of them right now. It's obviously an architectural decision to be made internally, but it's an important one. How are you going to handle schema evolution and rule changes? It's not a problem to build these things on top of your loading logic. And I think that that's one of the nice ways to solve the problem. When you're thinking about data science, you might want to run certain graph queries or create certain features that you want to store back on the graph. And finally, an interesting problem is really data privacy, which I have something to say about in a minute. But I think first, I'll just talk about my company, Knights Analytics. So if this has been a kind of interesting topic for you, but maybe a bit too much to take on, then the goal of my company is actually to try and make this as easy as possible. So we've essentially built a graph engine which consumes data and solves a lot of the problems that I mentioned, such as mapping the data to triples, resolving entities, and applying business and logic and rules, and loading it into Dgraph. And that means that we've built our software in line with a lot of Dgraph's principles. So we wanted to be graph native, hence we wanted to choose a graph database that could keep up with our software. And we have a Kubernetes deployment. We're scalable, highly available. We support streaming and batch. And of course, we try to integrate with the big data landscape as much as possible. And some unique things about our tech is that we have our proprietary entity resolution algorithm. We can extract semantic relationships from unstructured data. We build and update the graph in real time, with an asterisk, because it very much depends on what real time means for you and your business problem. But so far we haven't had a problem. We integrate mapping data into our engine with a kind of a standardized interface, and we have a number of pre-built models for industry problems, so both in terms of extraction of the data and the mapping to an ontology. And of course we're able to expand that without interruption. So I'm going to finish on something I think is really interesting and exciting, hopefully, which is that we've been working with a company called Roseman Labs here in the Netherlands also to be able to do privacy preserving network graphs. This is important for a lot of banking and money laundering use cases where we really want to be able to share data and analyze data and detect financial crime, but we're not able to do some of the more fuzzy entity resolution. I don't have time to dive into this topic because it's a big one, but if you want to know any more, then feel free to reach out to me or to them. We'll be happy to talk about it. But other than that, that's it for me. If you want to contact me, here's my email and my LinkedIn. Otherwise, thanks for listening.